Hey, my name is Raj Singh, a computer engineer here at Iowa State, and today we're going to be going over Quic Semantics. So, what is Quic? Quic is a transport layer protocol, which stands for Quick UDP Internet Connections. It is designed to improve the performance of HTTP over the Internet. It uses UDP instead of TCP for data transfer, which allows for faster and more efficient communication between clients and servers. So you may be asking yourself, why, Raj, are we even replacing TCP? What's wrong with it? Well, in the 1980s, when it was first designed, it was designed around single file transfer, where web pages only had some HTML, some CSS, and maybe a little bit of JavaScript. Nowadays, there's a lot more overhead. There's TLS, which is for secure connections, and there's some API calls you might have to make, and maybe some images that you have to load. Well, TCP was not originally designed for that. So Quic provides several advantages over this. This includes faster connection setup, improved congestion control, security enhancements, and improved error handling. It also solves the issue for latency and lossy slow connections, using smart packet loss data dropping while also integrating tightly with TLS. And Quic also corresponds with HTTP 3, which already had header compression, but now has updated it to something called QPAC. There's multiplexing, which enables multiple network requests over a single TCP connection. There's resource prioritization, which allows essential resources to be loaded first. And server push, which lets the server send data to the client before it even requests it. We will go more into the details of how this all works and why it's so awesome. So I pulled this image directly from Cloudflare, which gets to see a lot of the traffic that flows through the internet today. And we can see that over a fourth of the traffic is already using HTTP 3. And you're using it and you don't even realize it. You can see the true latency comparison between TCP and Quic on the image on the right. You can see how much faster that truly is to set up that connection. Recently, all the HTTP related RFCs were redesigned to separate out the different HTTP versions. The main ones we're going to look at here are QPAC and extensible priorities. I like this slide because it really shows that HTTP 2 and HTTP 3 are really quite similar. They do very similar things. There was a much bigger difference between HTTP 1 and HTTP 2, which brings up my point of HTTP 3 isn't what we really wanted. We wanted Quic. And what Quic is actually more intended is to be the replacement for TCP. So TCP, your bread and butter protocol that is most things used on the internet, you may ask yourself, why don't we just update TCP to do Quic features? In practice, this turns out to be way too difficult. And so they kind of made a new version called HTTP 3, which has the exact same features of HTTP 2, but I should say implements them in a very different way. So the common misconception is that it's faster because it's using UDP. And it is faster, but it's not because it is using UDP. It's because it's doing smarter things or doing more things. It's not because of UDP. UDP is only there because middle boxes like firewalls and routers expect TCP or UDP. Any packets formatted differently than this will probably result in dropping those packets entirely. If we try to run Quic directly on top of IP, it's possible, and there's no technical reason why that's not possible, but practically and deployment wise, you would also have to update a lot of those middle boxes along the way to suddenly expect that. So the designers said, no, let's not do that. Let's just run it on top of UDP. Because most appliances at least speak UDP and know what UDP is. That indeed makes us run on top of UDP, and we're deeply encrypted and prevents us from the middle boxes messing with our traffic. And that allows us to be much more flexible in the future And that's why we can't just have like a TCP 2.0 because that would take years to deploy. So what Quic is going to do is going to deeply integrate with TLS. TLS is no longer an optional protocol when using Quic. It's deeply integrated inside of the protocol. What Quic is going to do is it's also going to encrypt the transport level headers. In TCP, you might have things like packet numbers or sequence numbers, acknowledgement numbers, flow control windows, and that kind of stuff. All the things that are in a TCP header, those are plain text visible on the wire. With Quic, that's no longer the case. As you can see here, we encrypt much more of the transport level stuff, including things like packet numbers, which were usually visible, and that reason, again, the hope that if the layer 3 devices cannot read this data, it can't interpret it, so they can't break the encryption. The firewalls can't read it, so hopefully they won't drop it if it's something they don't expect. So one of the biggest features that Quic implements is greatly increasing the handshake time frame. TCP, the previous version of this, starts with a three-way handshake, the SYN-SYN-ACK handshake, that takes a full round trip on the network. And especially if your client and server are far from each other, that round trip can take about 200 to 300 milliseconds. It's not just that. After this, you also have the TLS handshake, which in older versions of TLS would take 2 round trips. Luckily, with the newer TLS 1.3, we can just get 1, but it's an additional round trip. And it's only after that you can actually start doing HTTP level requests, like send your first request and get a response back. So in these situations, even with TLS 1.3, you're raising 3 round trips, sometimes over half a second before you get any useful data back. The biggest problem here is that everything is nicely and cleanly separated. The protocols don't need to know about each other in order to function, making it inefficient. What you can really want is a kind of like the third column here, where you would actually combine the TCP and TLS handshake in a single round trip. But what you actually want is the fourth column. Why can't we just do everything at once? Combine everything into a fully complete round trip. And that's now actually possible with Quic, with a feature called 0RTT. And the idea there is that the first connection you have to a Quic server that you haven't seen before, that has to do the 2 handshake, but during that connection, you can actually negotiate encryption keys for the next connection after that. And so if you do the next connection to a server that you've already known and your browser has already remembered those encryption keys, then you can immediately encrypt your first HTTP request in the first round trip. And so you can combine all 3 layers, the transport, security, and application layer, all into a single round trip and get a lot of data in earlier. And that is what I would say is the killer feature of HTTP 3 and Quic. Another feature that Quic implements is the idea of packet handling. So the first row here, TCP, as you may know, it doesn't actually have packet numbers, it has sequence numbers. So basically, TCP thinks it's only carrying 1 byte stream. TCP was initially designed for single files, as we mentioned earlier. Nowadays, we don't just have 1 file, we have multiple. In this case, we have 2. We have a CSS and a JavaScript file. We both want to download these over a single TCP connection, but you can't do that because TCP doesn't allow more than 1 resource at a time. And that was one of the big problems with HTTP 1. And so what HTTP 2 would say is, okay, we're going to introduce the concept of independent byte streams at the HTTP 2 layer. It says the CSS file has a stream ID of 1 and the JavaScript file has a stream ID of 2. So those are different. 1 and 2 are different, and we have separate resources. This means that when you get this data back, the browser can decode this. They can know, okay, the coming 450 bytes are CSS, and the ones after that, the 300 bytes, are JavaScript. And they need to be handled differently. And this works fine. TCP doesn't have to know anything about this, and we can send multiple resources on one connection. The problem becomes is when the middle TCP packet gets dropped, and there's some problem with the network maybe, or the center packet is lost, but the third packet does arrive. So conceptually, at the HTTP2 layer, we know that the browser knows that the CSS stuff is actually not interrupted. We had the first 450 bytes come in, and the next 550 bytes, we have that. Those are there, and we can process all of the CSS data. It's only the JavaScript that has been delayed. That's the only one we should wait for retransmission to come in. We know this at the HTTP layer. TCP did not notice this. TCP thinks it's only sending one file. It only has one byte range there. And so it loses the full byte range 450 to 749. It doesn't know any data after that might be independent from the central packet. And so what it has to do is be conservative. It knows that the center packet is lost. Everything after that might depend on that same center packet. And I'm going to be careful and not process anything after the lost packet until retransmission comes in. You leave a little bit of performance on the table here because the CSS could have been processed before the retransmission came in, and that is what is called head of line blocking. So you have to replace it at the head of the line before everything else can proceed. So in other words, the CSS gets delayed even though it's not necessary to delay it while we're waiting for that piece to come back. The head of the line is delaying all the others, and that's the main problem here with TCP. So what Quic does is it takes the concept of these streams, so the stream IDs that we had in HTTP2, and it takes those from the HTTP layer and brings them down to the transport layer. And so you get a comparison like this, where the stream ID stuff tracking which bytes belong to what stream no longer is done at the HTTP level. It's done at the transport level. So now Quic suddenly knows there are multiple independent streams going over the network. Quic has actual proper packet numbers, packet 1, 2, 3, not sequence numbers that are sometimes definitely difficult to follow, especially on things like Wireshark. Quic uses what are called stream frames, which are basically saying, okay, for this stream, we now have byte X to Y, so in this case byte 0 to 449 for stream 1, and the next packet carries JavaScript that starts again, that is bytes 0 to 299. Because it's specific for JavaScript stream number 2, if in Quic the second packet is lost, Quic will then receive the third packet, and it can see, okay, the first packet head bytes 0 through 449 for CSS, and the third packet byte 450 has no gap for the CSS, and that can be processed. TCP was never clever enough to handle that if one of those goes missing by having the separation of streams on the transport layer, then this leads to other Quic benefits like smarter loss detection and usage. Quic doesn't need to retransmit full packets, it just retransmits parts of those packets if it wants to. And this is one of the key points that I think makes HTTP 3 plus Quic faster, is that Quic can, for example, in HTTP 3, we have the concept of stream priority. So some files are going to be more important than others, and your JavaScript and CSS are going to be more important than, say, an image file on the bottom of your page, at least at the beginning. My personal favorite feature that Quic has implemented is the idea of connection migration. Say you have a cell phone which is connected through Wi-Fi to your office, for example, but then you move outside to the parking lot and it's time to go home. You move out of range of the Wi-Fi and your cell phone automatically switches over to a 5G network. And that works. The problem is from a TCP standpoint, you suddenly switch WAN IPs, causing the 5G network to be completely different from that Wi-Fi network. And the way TCP connections work, it just looks at the client and the server IP and the TCP port and the client port. So when the client IP changes, because we change networks, any TCP connections you have in that instance are going to have to be shut down and not able to be used anymore. And so you need to re-establish all of your TCP connections from the start. So you need to do all the connection setups again. You need to warm up your congestion window to get a better data speeds again, and so on. So what Quic does instead is it will use what is called connection IDs. So each connection ID is not just the IPs, it's also a unique number. And then when you move between networks, it will keep this connection ID the same. Because we can keep that constant, even though the IP and ports changed from switching from Wi-Fi to cellular or vice versa, the connection ID is exactly the same. So the server knows, oh, this is the exact same client I had before, and we can keep the same connection. We don't need to do any new connection setups, and the way that works is by including this connection ID in every packet. And that's actually one of the few fields that are not encrypted in a Quic packet header. And it's going to still result in a much better experience than using TCP because you're not resetting your connection all the time. So to give you guys a more real-world example of the differences between TCP and TLS, as well as understanding kind of how this packet is actually being, distributed on the wire, we can see here when I'm hitting my personal website, rajsingh.info, the TCP and TLS handshakes going on. We can also see the TCP packet, and we can see the port number, the destination, the sequence number, the acknowledgement number, where most of this would be encrypted on Quic. So if we go over to something like cloudflare.com, which I know is using probably a more updated server than me, that my web browser has accepted using Quic. And we can see on the actual packet information that we have our generic payload, and we just have our port numbers and our checksum and just our connection ID. And that's about it. Everything else is encrypted, and there's nothing else to really see here. We can't see the TLS handshake going on, and of course we can't see any of the data.